Thank you very much, Amber. Today's presentation is regarding one of the topics and one of the most commonly asked questions we have surrounding life of rope, particularly HMPE Dyneema rope. It's the question of creep, or the phenomena of creep, I guess. And today I hope to explain that a little bit better, dispel perhaps some of the misunderstandings surrounding it, and be able to explain the mechanisms a little bit so that when and if the question arises, well, tell me about how the rope creeps, you're armed with some good facts and a solid understanding of just what's taking place and what does that mean to the user. Quick little background, since this presentation will be focusing primarily on creep and Dyneema. Dyneema HMPE rope, as you guys know, such as Amsteel Blue, it's one of the most versatile, strongest, lightest weight ropes on the market. You know, we use it in a whole host of industries, from commercial marine applications such as mooring and tug, to winching lines, to mining, to recreational marine. It basically provides outstanding performance in the form of strength, stiffness, long life, and of course, due to its lightweight, unmatched safety when compared to things like steel wire. However, the phenomena of creep taking place in the material has caused some concerns as to how and when the rope is properly used, as well as when to retire the rope in order to avoid any potential failures. So we're going to dive into that a little bit. Hold on a second. There we go. First of all, a quick definition. Creep is an intrinsic material phenomena that takes place that is a very, very slow and permanent deformation of a solid material when it's under a stress. So basically, I'm pulling or pushing on something, and it's going to continue to elongate or shear. Creep in other cases is known as cold flow. One important thing to note is that creep occurs in nearly all materials, all solid materials, to one degree or another. The difference is the mechanism by which that creep takes place can change dramatically between materials, and the rates and the extent to which it happens can change quite a bit. And this is really a material property. It's not so much a rope property. What's actually happening is there's dislocations or sliding taking place between the long molecules that make up the polyethylene polymer or macromolecule. So in the case of an HMPE creep, what you have are these chains sliding past each other. To give it a quick analogy, if you imagine that polyethylene, individual polyethylene molecules look like long pieces of cooked spaghetti. If you were to take a block of just high modulus polyethylene, I'm not talking about the fiber right now, but just a block of HDPE, what you'd essentially see on the microscopic level is a tangle of these polyethylene chains. Now, what happens when you draw the material to make a fiber is these chains tend to line up, similar to when I'm lifting my spaghetti out with a fork. I'm pulling on it, and because I'm pulling on these chains, they tend to slide a little bit and line up. This is what imparts great strength to the Dyneema fiber. However, those individual molecules aren't very, very well fixed to each other. They're not what we call cross-linked. And so they're still capable of having movement relative to each other. And that's generally what's happening when the fiber is creeping. Under load, there's always a chance that one of those little fibers can slip, or one of those little molecules, not even a fiber, it's a molecule, can slip past its neighbor just a little bit. So similarly, if I'm lifting my fork up out of the bowl of spaghetti, those spaghetti strands are sliding past each other a little bit, up until the point when eventually they slide so far past each other that it disconnects, it breaks. I can put the fork full of spaghetti into my mouth and leave the rest in the bowl. So how does creep happen in HMPE? What we tend to do is break down the creep into 3 different stages, and they're described as primary creep, secondary or steady state creep, and the tertiary creep. This graph I'm showing here illustrates basically the elongation due to creep over time under a constant load. It's important to note that this graph is not to scale in any way. It's just designed to illustrate roughly what's going on. What we see here is on the left-hand side, upon immediate loading, you see this primary creep phase, which happens quite rapidly. And when I mean rapidly, it's anywhere on the order of hours to weeks, generally, depending on the usage. After which time the creep rate slows down and reaches that steady state creep where it's kind of progressing upward at a constant rate. This steady state creep is really the bulk of time. This can be anywhere from weeks to months to years, depending on the specifics of the application. But this is generally where most of the creep strain is taking place. Finally, as you approach the end of that steady state creep, you hit the tertiary region. This is where the creep begins to accelerate. This is essentially akin to where those strands of spaghetti start disconnecting from each other. Now you have fewer and fewer bits holding together, and so the creep rate begins to dramatically increase and failure is imminent. So generally when we talk about the time to retire due to creep, it would be at the end of the second phase. You wouldn't ever want to go into the third phase. That's considered being in the danger zone. So to break it down in a little bit more detail, this primary creep, this is that rapid elongation. And what you really have taking place here is not so much the chains sliding past each other yet, or the polymer chain sliding past each other, but rather there's a slight reorientation of what we call the amorphous zones. So most of the fiber, most of the material that makes up the rope is what we call crystalline or pseudo-crystalline. The molecules have very specific locations next to each other. They're basically all standing in line. You do, however, have small regions where there's still a tangle exists, that they're not all standing in line nicely. They're still kind of mixed up like the spaghetti in the bottom of the bowl. So when you first load it up over that first days to weeks, sometimes hours at a high enough temperature, what you see is those amorphous zones kind of straighten out and elongate. And this takes place, like I said, pretty quickly relative to the steady state creep, but it does quickly peter out. Important to note is this is often the quote-unquote creep that's observed by a user in the field. So if you were to take a piece of Amsteel blue, using it as a halyard, and you were to tension that halyard, and a short while later it seemed to have slacked off or lost tension, people go, oh my God, it's creeping. And they expect that that rate of creep would continue. It will not. Basically, that portion of it might be, a percentage of strain or a percentage of elongation before it stops growing and slows down and really hits that slow zone, which is orders of magnitude slower than this rapid part in the beginning. Now that slow zone is this secondary creep. This is really where those polymer chains, which are already standing in rows next to each other, nicely in line, begin to slide past their neighbors. And this rate is, assuming that the temperature and the load are the same, this rate is going to be constant over time. And like I said, it's going to be anywhere from 10, 100, 1,000 times slower than that first initial bit. This secondary creep is really mainly of a concern to applications where there's a long-term steady load, or there is a high temperature, or a combination of both. The truth is, for most applications, for example, if you're using it as a main line on a tugboat, you're never, ever, ever going to see significant creep, though it's just not loaded long enough. You're going to have failure due to other mechanisms. But let's say you're going to have a mooring tether for a floating offshore oil platform that's got a design, that's got an operational life of 10 years and a design life of 50 years. Then yes, you would observe significant amounts of creep. And finally, as you hit that tertiary stage, this is where I said where again the creep rate begins to pick up. And really the point of failure is oftentimes hard to predict. It can happen kind of randomly within that tertiary zone. But so generally we say that once you've reached the onset of that tertiary zone, it's done. It's end of service life. And this tertiary phase can begin anywhere between 10 and 30% of elongation due to creep. Therefore, the safest thing to say is if the rope had gotten 10% longer than it was when it started, it's done. It's good to say you can put this away. Like I said, when this onset takes place depends on the temperature and load history. It's impossible to have a one number that covers all scenarios. It's a quite complex nonlinear phenomenon. Now, an important distinction to make when people ask about, oh, is this rope creeping, is the distinction between what I would term as observable rope responses, or things that a user can see or measure on a rope, versus the physical mechanisms that cause these observable rope responses. And I put creep in there as a physical mechanism. It's not something you can directly see. You can't actually see the molecules in the fiber moving past each other and doing their thing. What you might see is the rope getting longer. However, there's other physical mechanisms that can also cause the rope to get longer. So I've created this table to kind of illustrate that. What we see is there's basically three kinds of observable rope response when I put a rope under load. There's the elastic elongation, or the instantaneous change in length with load. I pull on something with a certain load, it stretches a certain amount. I release the load, it gives back a little. Now, we generally don't think of a Dyneema rope as being very stretchy, as opposed to a rubber band, but essentially they are behaving in the same way. It's just a much, much, much stiffer rubber band. And this is primarily caused by the elasticity of the material. It's a material property, as well as there is some of this constructional deformation of the rope. So the geometry of the strands of the fibers of the rope changing as you pull on it, it tends to compact and get narrower, and you release it, it wants to move back out a little bit again. The second type of observable rope response is the permanent elongation. This is when I pull on something, it gets longer, I let it go, it does not recover, or it does not snap back. This is plastic deformation. And this, again, there's a certain property of the material, which is its plasticity. There's also creep that can contribute to this if it's slow. Plasticity takes place instantly. If I pull on it and I can stretch it and I let it go and it doesn't pop back, that's a plastic deformation. Creep is a special type of plastic deformation that takes place slowly over time. Again, there's permanent elongation due to constructional deformation. If you would load up a rope a number of times from when it's new, it tends to pack in and set. And as it sets, the diameter decreases slightly, the length gets longer. And finally, the last type of permanent elongation that a user might often see is the splice setting. So after you've spliced the rope and you've loaded it up a couple times, oftentimes there's a little bit of slippage in that splice as everything kind of gets set in its best position. That may lead to a slightly longer length than when you spliced the rope and you thought, hey, I made this 10-meter long piece of rope. It might be, 10 meters plus a couple centimeters. And the final type of observable rope responses, of course, we call hysteretic or recoverable elongation. This kind of lives halfway in between the world of elastic and plastic. The elastic is instantaneous, the plastic is permanent. Hysteretic is one of those things that kind of slowly recovers. It's like a gas shock absorber. You push it down, it doesn't pop back up right away. It kind of slowly comes back. And that primary creep that I discussed early on, that is somewhat recoverable. As I said, it's that untangling of the chains and kind of setting them in line. Well, you let it sit around, those molecules are always moving. As long as you're at some temperature above absolute zero, there's always a little wiggle in those molecules, and they tend to disorder themselves slightly. Wrong direction. So what are the implications of this? There's really two reasons why creep may be an issue to a user. The first thing that comes to mind for most people is it going to rupture? Is my rope going to break due to the creep phenomena taking place in my fiber? And the truth is that really, for most cases that we see users using our rope, and that's not going to happen. It requires long times, high temperatures, or high loads. As I said, it's really a concern in these static applications where there's an installation put in place that is going to remain under load for large periods of time, or it's at a high temperature. If there is any scenario like that you encounter with a customer or potential customer, and you need some advice as to what is the expected lifetime or the creep lifetime, we can certainly do those calculations, and you can get in touch with us, and working together with DSM Dyneema, we can get a pretty accurate model along with uncertainties and tolerances in terms of how long you can expect that rope to last under a certain load. But as I said, in most dynamic applications, there's other causes of failure going to dominate, whether it's abrasive wear, whether it's cutting, whether it's overloading or shocking. Is really the case. Now, the other thing that can take place, which can sometimes be a concern to a user, even if the rope is not going to break from creep, is just the fact that the creep elongation takes place. So oftentimes you might need a very precise length. For example, my halyard example, you don't want that halyard necessarily to stress relax or elongate under load. So this can be troublesome. This is, like I said, it's often manifested as a relaxation of a tensioned rope. And if this is the case, there's other fibers that can be used to mitigate this phenomena. As I pointed out in the very beginning, creep is something that happens in almost all materials, or creep rupture is something that happens in almost all materials. The difference between something like polyethylene, Dyneema, and some of the other high-performance fibers is while they have a creep rupture as well, before they break, they usually will have stretched much, much, much less. As I said, we generally consider the end of useful life to be about 10% strain due to creep on Dyneema. With an aramid or a LCP or another high-performance fiber, you might only see 0.5% strain before that rupture takes place, but the phenomena still does occur. So, what can we do about this if we say we want to use Dyneema? Dyneema is the best fiber to use for our particular application, but we may have a concern with creep. What are our choices? Well, SK75 fiber is kind of the performance standard. This is the fiber that we use in Amsteel Blue. And like I said, it's an excellent choice for all-around use for dynamic applications where creep's really not going to be the primary cause of failure. If there is a scenario where creep is of a concern, DSM has a second fiber that's called SK78, and this is their reduced creep fiber. They've modified the production process slightly, and it reduces the creep rate to about 25 or 50% of the SK75 creep rate, while maintaining every other favorable property that you find in Dyneema: the strength, the lightweight, the toughness, abrasion resistance, etc. So this is a good choice for applications where, hey, it's a bit of a concern, we want to address it, and we can significantly slow down that creep rate and increase the lifetime. Finally, the DSM Dyneema has just released a brand new fiber, which they call DM20, which is their ultra-low creep fiber. Now this is a complete change. They actually went ahead and changed some of the chemistry in the fiber as well as the production process, and this has led to creep performance on par with fibers such as the aramids. So it is going to have a negligible amount of creep strain over its lifetime. That doesn't mean it won't have a creep failure. It will. It'll last much, much, much longer than SK75 or SK78, and it won't be stretching in that time. But like I said, it will happen to everything. But so far, this fiber is brand new. It's primarily being aimed right now at creep critical applications such as offshore mooring. So we don't anticipate at this point to start selling Amsteel Blue made of DM20 quite yet. But we are investigating markets for that fiber. And if you have any other questions following this webinar, I guess Amber's email is there, or I guess we're going to take a look if anyone had any questions from what I've presented so far.
We'll give everybody just a moment in case they do have a question to type it into the box below. It looks like no one does have any questions right now, but that was a great presentation. And again, it will be, the recorded version will be made available on our customer portal, and I will put the information out there and letting you know when that will be available. I'll send you all an email and note it on the portal. So it looks like we don't have any questions. That's great, Greg.
Oh, here we go.
Oh, there's one coming in right now.
Let's see if I can read this. Okay, first question is creep in Spectra. Yes, Spectra is fundamentally the same material as Dyneema. They're both polyethylene or high modulus polyethylene. They differ mainly in the production process, but materially they are the same. So Spectra will have a very, very similar creep behavior to what I described in this presentation. Now, being that we don't sell Spectra, I'm not privy to the detailed calculations of estimating Spectra's creep life. But yes, it takes place pretty much by the same mechanism. Another question here is, how critical is the ambient temperature on this creep? It's very, very critical. Basically, temperature is the key factor in determining what the creep rate is, and it's highly nonlinear. So if I double the temperature, I don't double the creep rate. The creep rate will run away as temperature increases. So, you know, keeping the temperature low is always important. And anytime there's a high temperature or a moderate temperature application, you need to start thinking, is creep going to be an issue? Now, it's generally not an issue when we're talking about, you know, 30 degrees Celsius or, you know, 90 degrees Fahrenheit. That's fine. But if you get into that range where you're up, you know, 50 degrees Celsius, 45, 50 and above, that's when you really need to start asking those questions of is this going to be an issue? And like I said earlier, if it is of a concern, feel free to contact us, and we can put together a model to estimate what the creep life is going to be under specific temperatures and specific loads. And then you can address it either by using a different fiber, or oftentimes you can also, if you were to upsize the rope, for example, you load it to lower percent of its strength, the fibers themselves are being stressed less, therefore you'll slow down that creep rate significantly. Let's see, there's a question. Can you email this PowerPoint presentation to all of us? Amber, can we?
We are going to have it available on the portal again, so yes, if you have any issue with downloading it, I can help you. So definitely get in touch with me once it's posted if you're having trouble getting it.
It says, is the recovery or rebounding decreasing as the rope gets older after its load is relaxed? Yes and no. So like I said, there's a number of different factors that can cause that recovery. It's not just that molecular motion, which is the creep. You also have the rope setting or packing in. That doesn't tend to be as recoverable by itself. You can always fluff the rope up, I guess. In terms of the actual creep in the filament, so on the molecular level, no, that rebounding is kind of always pretty similar. But note that recovery is rather a small amount of strain, maybe 0.5% or so. And again, that's also dependent on temperature. So if something is warmer, it would recover faster because those molecules are wiggling around a little bit more. There's a question here that says, can we get samples of each of the 3 types of rope presented today? Well, 2 of them you can. So SK75 fiber is the fiber we use in the majority of our Dyneema ropes. The SK78 fiber is used in a number of ropes. The simplest one would be we have a rope called AS78, which is basically Amsteel blue made of SK78 fiber rather than SK75 fiber. We do also make a number of our other ropes. For example, the Turbo 75s you can get with an SK78. A lot of these offshore ropes are available in SK78. And so since they are very, very similar in behavior, in theory we could make any of our Dyneema ropes out of the SK78 if there's a need for it. The DM20, like I said, is brand new. DSM just released this fiber to the market a couple months ago. They made the announcement. They're still ramping up production. So we currently don't have any products made of DM20 yet. We're still investigating where it fits the best. Does heat treating fiber affect creep in rope? That's an excellent question, and I want to smack myself for not addressing this in my presentation. Yes, 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 and yes. Basically, what heat treating does is, in effect, pre-creep somewhat your rope. What happens is that, like I said, the creep rate is affected tremendously by temperature. So heat treating or heat setting, what people do is they elevate the temperature of the rope and they stretch it, and they basically creep it out somewhat. And why does that make the rope stronger? Well, what it does is, if you imagine when you make a rope, you have thousands to millions of little individual filaments, and they're all carrying a few grams of load. in a perfect world, to have a very, very efficient rope, you'd want each one of those little filaments to carry, everything it could. They should all be carrying the same amount of load, and they should all fail simultaneously if you were to continue to ramp up the tension. However, in reality, that's very, very difficult to do in production. And what you end up getting is some filaments are carrying a little bit more weight, and some of them are acting like slackers. They're not doing very much. They might be buckled slightly or bent. When you heat treat a rope and you pull on it under temperature, those filaments that are carrying more of the load will creep faster, and therefore they stretch out, allowing the neighbors, which are slacking, to begin to pick up the load. So you've essentially creeped the rope somewhat, making it stronger. The downside is you've now taken out some of that creep life. There's a set amount of creep life in the fiber, and you've now gotten rid of some of it. So a heat set rope generally will have a much shorter creep life than a non-heat set rope. An interesting phenomenon we see with non-heat set ropes, for example, on Amsteel Blue, is putting it into the field and using it. When we bring back used ropes, we oftentimes see ropes that are significantly stronger than when they left the factory. They may be 10, 15% stronger, even though they've suffered some abrasion. And this is primarily because in use, you are essentially slowly doing the same thing. You're equalizing the load of each of the filaments, kind of like what a heat set does. A good analogy given by Bill Franzalia from DSM Dyneema, he said, heat setting a rope is kind of like stonewashing a pair of jeans. You get them straight from the store and they're nice and soft and comfortable, but they'll wear a hole they'll get a hole worn in them a lot quicker than if you buy your crispy, crunchy, brand new Levi's that takes a while to break in. In the Northwest Australia, we have rope working in 50 degrees C. Is that the whole question? Yeah, that's a pretty significant temperature. And if there's concerns about being loaded for long periods of time under temperatures that high, we should certainly talk some more and see how we can best mitigate any risks. Once a line has gotten to a percentage of load, it never exceeds that percentage. Let's see, what does it say? Once a line has gotten to a percentage of load, if it never exceeds that percent again, will it still creep? Yes. The creep is really a function of what's of the stress and the temperature in the material at that time. There's not so much of a memory effect necessarily, if I understand the question correctly. What about heat set and pre-stretch products? Is that just a marketing ploy? No, I don't think it's a marketing ploy. I think it's a very realistic thing. You, like I explained earlier, you're essentially balancing the load in all the filaments better, thus creating a rope that is stronger straight out of the factory. However, you're decreasing its life. And if you don't heat set the rope, but you use it under tension, you will realize very, very similar effects. You're going to pack in that rope, it's going to compact in, and it's going to become stronger over time. It's just that you're gaining the benefit of the full creep life of the fiber. You haven't, worn away 30% of its life before it even left the building. Let's see. Next question. Is there a temperature chart relative to creep? No, not one that's available. Like I said, it depends on a number of factors, including your stress and your temperature. So it's a rather complex curve. So there's not one chart that captures all of it. Basically, if there's a need for estimates, if you contact us here in the engineering department, we can run some computer simulation that will output the creep rate over time as well as the overall creep life, and it's going to be bounded by uncertainty because, of course, you run the same experiment twice, you never get the exact same answer. So not only is it going to tell you what the average creep life is, it'll tell you what the minimum and maximum you can expect based on all the data that DSM Dyneema has gathered regarding this the subject. And so no, it's not easily captured in one chart, unfortunately. All right, I think that's, I don't see any other questions here, so I think we got it all. And again, we are available here all the time to to address any sort of questions you may have regarding this. So feel free to give me or one of my team here a call, and we'll gladly try to address any technical questions or challenges you might face. And you guys all have a great day and happy holidays.
Thanks, Greg. Thanks, everybody. Have a great day.